Welcome back to Advent of Code 2024, day 9. Um, yeah, starting a bit late today. Had a flight to catch. And I wasn't sure if my hotel would have good enough Wi-Fi, but it does, so I can keep streaming the next few days. You never know. Welcome in, Smab UK. I assume you must have done this already. All right. Hang on. All right, so wouldn't be watching otherwise. Yep, fair enough. Day 9. Day 9, Disk Fragmenter. Another push of the button leaves you in the familiar hallways of some friendly amphipods. I just realized that we never had a Wikipedia link this year. It was only references to past problems. In past years, they had a lot of Wikipedia links, as well as a few references to past problems. I guess we've learned all we need to learn from Wikipedia by now. Familiar halls of some friendly amphipods. What's an amphipod? Let's check the past year. Oh, this has a Wikipedia link, though. The past problem does. Amphipoda. An order of malacostracan crustaceans with no carapace. That's like the shell, right? I know that from Morrowind. You can get armor, which is like a carapace. You get from insects. And generally with laterally compressed bodies. Suppose that's because they're deep in the ocean. Looks tasty. Alright. Good thing you each somehow got your own personal mini-submarine. The historian's jet... Hello, Povijaro. You have nice programming streams videos. Have you tried Everybody Codes? I've heard about this. In fact, I read a couple of months ago I saw someone talking about it, and just the other day I saw someone talking about it again. It seems like it's an alternative to Advent of Code. Does it run... Do they have a set time during the year when they do events, or is it... Are they doing one like a Christmas one, or... But yeah, I mean, it will be good to give myself more options to do throughout the year, because now that I've exhausted almost all archived years for this, I need to look for other things to do during the year that I can stream. So yeah, I think maybe in a couple of months' time I might actually go and do Everybody Codes, like whatever the most recent event was. But is it, like, have you done it yourself? Is it pretty similar? Where was I? The historians jet away in search of the chief, mostly by driving directly into walls. While the historians quickly figure out how to pilot these things, you notice an amphipod in the corner struggling with his computer. He's trying to make more contiguous free space by compacting all of the files, but his program isn't working. You offer to help. Oh man. This takes me back. Remember the days when we had to defrag our disks? Is it even still an option in Windows? Let me see. Defrag... Oh, it is! Defragment and optimize drives. Makes sense that you would still have it. I mean, it's a legacy thing, but it still serves a purpose, I suppose. It's very similar to app into code. Well, that's good. I want something very similar to app into code, and there isn't much out there. I mean, it's not exactly a profitable... I guess the reason there aren't many things like this is because it's no longer profitable. Or at least it's not as profitable as it may have been in previous years. So whoever runs it has to have a lot of passion and be willing to put the extra time and effort into it, even if they don't make up, enough in donations to make up for it. So I would guess whoever's running Everybody Codes has the same vision. Not everyone has SSDs. Yeah, that's true. And plus, even on an SSD, I assume it's still, like, you may well want manual control over that. But I meant more that I assumed Windows just does it behind the scenes without there even being an option to do it manually. But yeah, apparently you can do it manually. But it makes sense. That's still something that needs to be done. He shows you the disk map, your puzzle input he's already generated. For example, it does do it behind the scenes as well. Oh yeah, I'm sure it does. Does it have that cool display that was just so satisfying to watch as you're seeing like extra contiguous space appearing? I generally find it useful against external disks. Yeah, that makes sense. Actually, I do have an HDD that I store my games on. And it is kind of full. So I could actually look into that. Alright. So that's a disk map. The disk map uses a dense format to represent the layout of files and free space on the disk. The digits alternate between indicating the length of a file and the length of free space. Okay. So a disk map like 1, 2, 3, 4, 5 would represent a 1-block file. Two blocks of free space, a 3-block file, 4 blocks of free space. Okay, so this is in order, in like memory address order. Okay. Nine block files in a row with no free space between them. Each file on disk also has an ID number based on the order of the files as they appear before they are arranged. Starting with ID 0. So the disk map 1, 2, 3, 4, 5 has 3 files, a 1-block file with ID 0, 3-block file with ID 1. Okay, fine. Using 1 character for each block, where digits are the file ID and dot is free space. The disk map 1, 2, 3, 4, 5 represents these individual blocks. Okay. The first example above represents these individual blocks. The amphibot would like to move file blocks one at a time from the end of the disk to the leftmost free space block. Which end of the disk? The right, the left end? Yeah, the left end, yeah. Well, yeah, of course. It wouldn't make sense otherwise. Alright. Oh! Oh, no, it is from the right end. But, okay, they're not shifting it. They are actually taking it and putting it. Oh, I see. Okay, so it is from the right end. Okay, but it's not being shifted. It's not being shifted one space at a time. It's actually being moved. Okay. Alright. So, okay, so we move 2 blocks. And then we move the blocks there, there, there. Okay. Right. Alright, so we do the same here. We end up with that. Okay. The final step of this file compacting process is to update the file system checksum. To calculate the checksum, add up the result of multiplying each of these blocks' position with the file ID number it contains. The leftmost block is in position 0. If a block contains free space, skip it instead. So there shouldn't ever be any free space within the contiguous array after this process. It should just be free space at the end. Okay. So I mean, so far I don't think there's any smart algorithm needed. It's a linear time. We keep a pointer to the next available free block. We're moving a pointer backwards through these, and each time we're swapping the free block with that thing, basically. So it's a linear time scan until the 2 pointers meet. Let me read this checksum again. Add up the result of multiplying each of these blocks' position with the file ID number it contains. So if we're storing the ID number, we would know. If we're storing a list of ID numbers, for example, we would know what is within it. The leftmost block is in position 0. If the block contains free space, yeah, okay. So 0 times 0, yeah, 1, okay. Compact the amphipod's hard drive using the process he requested. What is the resulting file system checksum? Alright, how long is this going to be? Quite long. Still, I think we're dealing with linear time here. So, these are all single digits as well. So blocks can be at most 9 spaces. So like the most it could really be is 9 or like, let's say 10 times the length of this. Which is totally fine. All right. Oops. Okay, so so disk map equals just whatever the first line is. Wait, we're not allowed to do that. That's a generator. F dot just to just take that. Okay. Oh, it does produce a list. Oh, no, wait. I had a colon which wasn't needed. Yeah, there we go. Okay. So... print disk map. It's big. Okay. So just do the obvious thing then. Okay, so I have a feeling that in part 2 they're gonna inflate the sizes of these blocks to the point where it's impractical to actually represent every individual block in the list. But just do it for now. Let's say memory equals list. Okay. For just keep, I don't know, just keep a boolean, like, okay, let's say for num in disk map, let's say block, wait, what were the terms they used again? File and free, okay. Is file equals true. So if is file also we want id num equals 0. Alright, Smab UK, see you later. Hello, Amaro. So we start with id num 0, right? Yeah. And then if is file, just say, wait, this is a string. Let's just make it into int x. This one was a bit confusing. Was part 2 more complicated? Because I thought part 1 was fine for understanding, but we'll see if I understood. Int x for x in fw 0. So we're just doing... I'm guessing for part 2, they're gonna like inflate the blocks like by 1,000 or something, so it's not practical to store this many. Part 2 is fine? Okay. We'll see then. So for in range num so we just put it in. Just say memory dot append id num, and then id num, just increase it. Else we just do that, but with free space, and then is file equals not is file print memory. All right, let's see what this looks like. With print memory like 100. Let's just do these to 100. Alright, so we've got 2 zeros, then 8 nuns, then 4 ones, then 1 none. And if we get zeros, I assume it should be fine. We should just add that. That should just be redundant. Okay, so that's fine. Next, we need to defrag. So let's just let's just do the 2-pointer way. There's probably other ways of doing this more efficiently. Let's say we have a pointer pointer free starting at the beginning, and pointer files pointing at the end. While true. So pointer free is just going to keep going forward until it finds a free block. Pointer files is going to go from the end backwards until it finds a file block. And then when they're both resting on their free and file, respectively, we just swap the data and then repeat, right? This is one way of doing it. So we want to break out as soon as the 2 pointers cross over each other. So let's say push P3 forwards while... Let's wrap this up as a method, because then we can return out of nested loops. So let's say define get defrag. I get to write a defrag method. Things I learned, Python can use emojis as strings. Nice. Defrag of a section of memory. While true, so push P3 forwards. While, let's say, P3 is strictly less than P files. Well, these have to be defined here. And mem P3 is not looking at a none. P3 plus equal 1. Do the same for P files. Should call it P file, not P files. P, and while I think it's supposed to say is not none and is none. P file subtract 1, So if they cross over, if p3 is greater or equal to p file, then we return. We're going to alter this memory in place, or do we want to create a fresh copy? We'll alter it in place. Return. Okay, so now so P3 is on a free, P file is on a file. Swap them, right? Does that match what they want us to do? Let me just read this again. From the end of the disk to the leftmost free space block until there were no gaps. Yeah, I think so. Okay. Mem P3 mem P file P file equals a simultaneous swap. Okay. So defrag memory, and then we want to find checksum of memory. How do we define this? Oh, it's each of the ID numbers, which are the numbers that are in the list, with the position. Starting from 0. For I num ID num, because those are ID nums, in enumerate mem result equals 0. Result, this could be done as one-liner actually, but keep it like this. If ID num is not none, result plus equal ID num. No. I times ID num. Return result. Print checksum memory. Let's have a look at this. Print memory 100. Alright, let's see. Okay, that's the original disk map. That's what the address space looks like. That's after we defrag. Looks good. That is the checksum. It seems maybe, I don't know, deceptively straightforward. Let's find out. I don't see any tricks here. It's just That's how it was described. Will be correct. Upon completion, two things immediately become clear. First, the disk definitely has a lot more contiguous free space, just like the amphipod hoped. Second, the computer is running much more slowly. Maybe introducing all of that file system fragmentation was a bad idea. Oh, we do have Wikipedia links. I was just saying at the beginning of the stream, we haven't really seen many Wikipedia links. Just references to past problems. The eager amphipod already has a new plan. Rather than move individual blocks, he'd like to try compacting the files on his disk by moving whole files instead. Yeah, this is what I originally thought they were asking. This time, attempt to move whole files to the leftmost span of free space blocks that could fit the file. Attempt to move each file exactly once in order of decreasing file ID number. Okay. If there is no span of free space to the left of a file that is large enough to fit the file does not move. Similar. I mean, this pointer method will still work. We just have to look at blocks. See, it would actually make more sense if I had defined it all in terms of blocks in the first place. It's just a list of blocks. Actually, it's not too late for me to just do that. No, because the way I've done it actually was better for part 1. Because we're moving... because it has granularity, we're moving parts of files. If we had stored everything in terms of blocks where it has a width, that would be better for part 2. But let's just do it the way we use the individual blocks, like the way we've done it. It doesn't look too hard. So we do the same except Alright, so first of all, we want this to return a copy because we want to reuse the past memory. So let's say, well, we could do it in place, but we can say, this map equals this map 1. Disk map 2 equals disk map 1. That makes a copy. Oh, no, what am I doing? Keep the disk map. Leave the disk map alone. Let's say memory. Let's call it memory 1. Memory 2 equals memory 1. Clean copy. Okay, just get rid of all these prints. So we can still defrag in place. That's more useful considering we're doing a simultaneous swap here. But we want a defrag 1. Checksum is the same. Yeah. It's just define, move these things up. So this is part 1. So defrag 1. We do it, and then we print the checksum. Alright. Then we've got part 2. So let's just copy that. All right, so okay. So we do that as before. We do that until p3 is looking at a free space. P-file is looking at an ID num. Okay, that's fine. So if that happens, and we get as far as here, then we're in the right place. We just need to move some things around. With regards to the free space, we need to figure out how much free space we have. Or at least figure out if there's enough to fit. Okay, so let's first figure out the size of the file. So just the temp equals the file while the temp is the same as mem the file the temp minus equal 1. So now ptemp should be looking at just the item before. So pfile minus ptemp is the size. File size equals p file minus ptemp. Is that right? So if it was up with 2, pfile would be looking at the second element. Ptemp would move back 1, then it would move back 1 again. The difference would be 2. Yeah. Okay. We're not going to be doing this. Determine whether file would fit in free block. So if all, so just check if all mem p3 plus k is none for k in range file size. So this will stop as soon as it sees a violation. So it's saying, yeah, if every one of it, so file size was 7, it's saying if every one of these 7 locations, starting with P3, is none, that means it fits. And this will short circuit early, which doesn't matter because we're talking about small numbers here. It's only ever going to be maximum like 9. They could have made the problem a lot more interesting if we were dealing in the thousands. We would have had to find more efficient algorithms, but yeah, it's going to be like maximum 9 or 10. Well, no, it'd be maximum 9. So if it is, then we say move file. for k in range file size. So this and mem p temp minus k. So starting from there, moving backwards, equals that. So we do the swaps again, might as well. Okay. Now after we do that, we need to make sure that we it doesn't matter because p file will now be looking at a free space. P temp will now be looking at a block, so we can just let the next iteration push them forward and back as normal. Or we could save them time by just jumping. We don't need to do that. Alright. Is that it? So we just do this again. So defrag 2 is not defined. Yeah, that needs to be named. So now it's not going to be, because the files are not intact, we're going to have gaps. So the indexes of things are going to be higher in general. Plus, there are going to be fewer large ID things being pulled back. So we should get a much larger checksum now. Like, it should be much larger. Shouldn't take this long though. It's still pretty much a linear. Oh dear. Oh. Ah, there's a mistake. It's going to keep using those same files and those same blocks. So with the free pointer, p3 should stay there. That's the next available free space. Reuse it for whatever comes next. P file has to move. P file minus equal file size. Whether or not we move it, we need to move p file. Well, actually, technically we only have to move it if we are not moving the file, but we might as well move it even if we are. All right, let's try that. So because, yeah, we don't want to touch that file again. It's just, it keeps trying that file over and over again. There we go. It should be instant. It's like 10 times bigger. Okay. More like 3 times bigger. Seems... No! Too high. Okay. Let me make sure I actually read this properly. Off by 1. Oh, I know. I know what the problem is. So, no, wait, no, that's not the problem. I thought that we could be revisiting a file, so we move a file back, and then as the pointer comes back, we could be revisiting that file and moving it back further. But because the free pointer always moves forwards, no, that could never happen. So we could be moving a file more than once, but yeah, that shouldn't be able to happen. I suppose I can try the example then, but why would... I don't see how it could be an off by one error. We know the checksum is... should be okay. I feel like they should... Well, they said it's too high, so it should actually be less. Okay. Like one of these could be off by one. If all of those are none, 3 plus k for k in range file size. So for k in range file size, 3 plus k, temp minus k. Got the right methods here. I didn't break the first one, did I? Let's check that number again. 635, 505. Yeah, it's fine. Okay, let's just try the test example. One 9283540. 1928 is correct. It should be 2858. That's what way off. All right, let's print it then. See what it looks like. Just print memory to... Maybe I've done something stupid like this is being affected by what's happening to memory 1, but that's the point of doing this. It should be a independent copy. Right, print to memory 2. So 0, 0, none, 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 1, 1, 1, none, 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 2, none, 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 3. That's right. 0, 0, 8, 8. What happened to 9? We left 9 alone. And we moved 2 of the 8s. Oh, okay. Oh, it looks like the index is off by 2? Or something like that. Yeah. P temp. So P file equals length mem minus 1. P file should be looking at the last 9 at this point. So it looks like the three blocks are correct, but how did we end up taking those two eights? Oh my god, I'm using temp. Yeah, that's the problem. We were off by 2. Well, it was off by file size. Three, 4, 1, 8. No, that's the same answer. It's still wrong. P3, P file, P file, P3. So we move the 9s. So it should look like 009921111, correct? Then there should be 3 7s after that. Okay. So something's still off. P file, P3, P3, P file. Also, when we're doing this, I suppose we can let's do P3 plus equal file size. This won't change anything. Shouldn't change anything. Wait, what? That fixed it? No, it didn't, but we got closer. But wait, why would... Okay, no, that's weird. Why has that happened? Mem P3 plus K... No, but that looks more wrong now. These pointers are not trustworthy. P3 plus equal file size. That should be correct. Oh my god, no, 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 no. That is only if we did... If we only... That the indentation is not right. That's only if we moved the file. If we didn't move the file... Hang on, hang on. No, no, no. P file. If we did move the file, then we move P3. Whether or not we moved the file, we move P file. Now we're back to 3418, but that's still slightly more correct. Okay, fine. Now what? I guess we just have to look at what happens when we get to 777. Is this the simplest example we have? Well, it's the example they've mapped out. Okay, fine. So where does it go wrong? 2, 1, 1, 1. So we didn't move the 7s. So let's say here we'll print. I want to know P3 p file. I want to know what is actually at p file. I want to know the file size. Okay, let's try that. So when we get to 7, it says the file size is 3. Hang on. Okay, so here, p3 is 2. That's correct. P file is 41. It's looking at 9. 41, probably correct. We know we've got a 9. File size is 2. That's correct. So we move the 9s. Then we move this 2 spaces forwards. So now it's that none there. Oh, I get it now. We shouldn't be moving p3 forward. Oh, let me read the description again. p3 shouldn't be moving forward at all. Okay, I got it. This is potentially going to take quadratic time now. Unless I map out the gaps. Well, we'll see how long it takes. Alright, so the problem was for defrag 2, we should be starting from the left of the entire array every time for p3. We're looking for a gap anywhere from the left. So it'd be more efficient if we actually mapped out the gaps, then we wouldn't have to do this pointer thing, which is going to take ages. I mean, what kind of numbers are we talking about here? Print. Let me just take these out. Print. Print length of memory. 2, 3, 4, 1, 8. Okay, we can do quadratic time. That's fine. The smarter way to do this would be to map out the blocks, store their widths, map out their blocks, keep track of where they are. Whenever we move something, we destroy that free block and replace it with potentially a new one containing the gap at the end. That way we'll know exactly where our gaps are. We know we can index them by size, so we can immediately look for a list of free blocks of size 5 and so on. That should all be good, but we're not going to do that. We're going to do it the dirty way. Okay, get rid of this. Get rid of that. So p file is that. Pull p file back. Yes, well, but not. Yeah, I mapped 3 blocks and files, but then I had to go to bed before finishing. Yeah, I mean, that's kind of what computer architecture is doing, isn't it? Like, you have all these linked lists which kind of like take 3 blocks and map them to the next one. So as soon as you want a new 3 block, you can like take the next one and you know their sizes and stuff. There's lots of efficiency there, which we're going to ignore right now. Hopefully it works. 3,000 times 3,000. Yeah, we can do that. P equal 0 is while it's greater than 0 and so we push p file back until we find a new file. That's going to be the next ID. Ah. So we could actually, okay, now, no, there's several changes we have to make. So they said in decreasing file ID order, this time we do actually have to check that it's the right ID. So actually what we want is we want ID num equals max mem. We start with that because you can actually move things back a little bit and then encounter them again. You don't want to do that because they specifically said move things back. We'll do this to be safe. So while mem file is not equal to ID num. Okay. Push that back. If while ID num is greater than -1, greater or equal to 0. If it reaches the beginning, just return. Okay. So find size of file should be the same. Here we can just say while it's equal to ID num. File size is that's correct. Now we want to find first free block to fit file. So we could just do a quick and dirty for loop here, I would say. Just say for p free in range from 0 up to p file minus file size +1. That's like the furthest to the right. That's the last possible free block that could exist. It's of size 1, but that's technically the last one. If this can mostly be kept the same then. If all blah blah blah, we move the file. Okay. Like we could skip more at a time. If one block, if the beginning of a free block can't fit it, then clearly the next one couldn't either. But it doesn't really matter. So we move the file. That looks right. Don't change that. So if we move the file, then we break out of this for loop. Whether or not we move it, we move file size spaces back. Okay. And after all that, id num minus equal 1. So this is now, p-file is making a linear pass backwards, and for each one we're taking p3 as a linear pass forwards. It's kind of quadratic. Let's try that. You can't max a none. Max. X for x in mem if x is not none. I thought you could. I thought you were allowed to include nuns. I thought they would count as 0 or something. 2858. 2858 is correct for the test example. All right, that sounds a lot better. Let's just print. Also, that was basically instant, so 00992.111.777, correct. Gap 44, gap 333, 4 gaps, and then the rest is just like how it was to start with. So we got 5s, 6s, and then 8s. Yep, looks good. Oh, that was it was instant because it was the test example. Now we have to see what the big one's like. This might take a few seconds. This is going to be like, could be like 10 million operations. But it should get done. Otherwise, we actually have to be efficient. I don't see why. No, we shouldn't have to. It's just quadratic for that should be fine. Unless we. So it's not. It's actually like 90 million. So it's actually like 100 million because we're multiplying by another, potentially up to 9 here. Oh no, don't print it. God. There we go. It's only slightly more. And before it was like 3 times more. That actually kind of makes sense. Like, in general, the greedy algorithms do have decent performance when it comes to defragging. That's why we often use the greedy algorithms and not try to. Big files now have low positions, yeah. That's true as well. Yeah, that balances out a bit, but correct. Okay. Yeah, it was fast enough. Took, what, like 20 seconds? But yeah, I mean, if you want to do this nice and efficiently, you should really be storing the concept of a free block of a given width. Then you're not actually storing all that. But that only really reduces the runtime by a factor of 10. But it's still good. I didn't think this was fun or difficult, just a bit tedious. didn't really take long, so I didn't find it tedious to code. Did you do a similar approach with like pointers moving back and forth? But you said you tried doing mapping free blocks. Did you actually finish that approach, or did you just go back to every individual piece of memory? Only be watching a few minutes, I'm not sure. Okay. I just stuck to individual pieces of data, so storing that as an array of individual ID nums and just moving the pointer back one by one, and then every time doing a for loop until I find the next free block. But it would be more efficient if I was storing blocks, gaps, then I could. So if I stored all the gaps in like a hash map, like 1 maps to all the free blocks of size 1, 2 maps to all the free blocks of size 2, and so on. Then if I want to move something of size 4 back, I would start from 4 in the hash map, find all the blocks of size 4, and if there are none, go to 5, 6, 7, like that. No, that's not right. You would have to, you would have to look for all the blocks of size 4, 5, 6, 7, 8, 9 all together, and then find them one with the earliest position. So there's so there's a bit of complexity there, because you could have lots of blocks, which could take longer than just going from the left sometimes, if the first block was actually quite early on. So yeah, it's probably not that much faster. I made a dict for free blocks and a dict for file info. Yeah, I mean, doing at least just that, having a map of free blocks and their size should definitely cut down by a factor of 10 or something. And because it would be a factor of 10 in both the file and the free, and that's like my double for loop, it would actually be a factor of 100 rather than a factor of 10. Factor of 81, I suppose. As the music keeps stopping, I never notice when that happens, and it just gets silent for ages. Okay. I thought it was a good problem from a algorithms point of view, even though it didn't really need any. Well, we did do algorithms. Like, even for loops are algorithms and can have complexity to them. So and there's a lot of theory behind memory storage. Like, there's a lot of stuff about trade-offs between different approaches for where you store them. Like trying to find the best fit can sometimes be bad, because you leave lots of little gaps, which add up to a lot of memory that just doesn't really get used. So sometimes it's actually better to be more greedy, or to be more naive when you're choosing where to place new files when you're storing them on a computer. At least the description was more understandable than that antenna thing. Yeah. I think a lot of people agree that was just not written well. Especially for people who aren't native English speakers. I saw some posts by them, they were just completely stumped. They couldn't decipher it. Yep. But there are directions he could have taken this for more interesting and complex part 2s. And we're kind of, day 9, we're usually around the point where we start getting some tough ones. So it's been quite generous and easy so far. Like, there's definitely a lot more complex stuff he could have done with this. Like, for example, these individual things could have actually just been represented like 1,000 items each for part 1, for example. In which case you'd be splitting up blocks. In the memory, you'd be splitting up blocks, say like taking the first 77 or something, and then you'd actually have to store the blocks and their sizes, because otherwise you just get your array would be too big. That wouldn't really affect part 2 though. All right. There's the private leaderboards. And there's Captain Coda's leaderboard. Quite a lot of participants from are keeping up to date from Captain Coda's leaderboard. Captain Coda is, I believe, busy for the next few days, so he might not be streaming this for a few days. Or I don't know if he's even going to do them. He might do them offline. Okay, I'm done. So yeah, I'll probably do tomorrow's problem. These next 3 days or so, I might not find the time during the day. So if I do, it might be around this time or even later. I don't know. We'll see. All right, thank you for watching. Oh, let me check if anyone's doing it. Like, this might be a better time for Europeans. Just waking up and... Well, I say waking up, but it's now time, and I don't know, like France, for example, it's just past the afternoon. They would have to wake up at like 6 AM if they wanted to do it on time. Okay, people are using the tags, that's helpful. A lot of people are doing Rust. Alright, Uncle Scientist. Path of Exile 2 seems to be popular. Oh, that released recently, didn't it? I tried playing Path of Exile 1. It's not really my kind of genre, but it did have one of the most crazy complex skill trees I've ever seen in any game ever. Well, let me see if I can find an image of it. Path of Exile skill tree. There it is. That's the skill tree. That's the skill tree for Path of Exile 1. I don't know what they've done for Path of Exile 2. Can't even load the image. Looks like one of those games that's so complex most people copy builds online and it defeats the purpose. I don't know, if they enjoy doing that, if they enjoy copying builds, then fair enough. I assume most people are doing a mix of doing a bit of copying and a bit of flavoring it themselves. All right, has it loaded the Twitch video? Okay. Yeah, let's go check out Uncle Scientist. Is that a picture of Isaac Newton? Okay. All right. Thank you for watching. See you next time. Bye bye.